Okay, so today we're talking about the periodic table. Um, I've heard some of my other chemistry professors say it's the chemist's preferred tool, that physicists love calculators, biologists love microscopes. We use a periodic table here in this course. And it's going to be very important to understand how to read it, to know all the parts of the periodic table, and just to help you understand some of the patterns and to better understand and better appreciate why our periodic table is made this way. I'll show you some other examples that show the same patterns, but perhaps not as well or not as conveniently. Is that all right for you, Dr. Hunter?
Sure is. Yep. I just think that there are some serious shortcuts a person can take in trying to figure things out if they begin to put a little bit of effort into figuring out how the periodic table is organized.
Yep, exactly. And so we'll go over some of the basics. So over here, I'm highlighting hydrogen. It's zoomed in. You can see that top number in the top left-hand corner of that box. That's the atomic number. Then we have the element symbol, the element name, and the molar mass of that element. And so that's for each element. And the table is organized by periods or the rows. So hydrogen and helium, they are in period 1, period 2, lithium, beryllium, and all these other elements I'm going over, and so on. And we also have the columns, which are the groups. So this is group 1, group 2. On this periodic table, they do 3, 4. Sometimes in other periodic tables, you'll skip from 2 all the way to 3 here, and it might be subcategorized as in A or B. Like this group 3 may be considered group 1B, and I'll go over that a little bit more. But basically, the periods organize the elements through energy levels. So this is the first energy level, second, third, fourth, so on. And the groups organize the elements by the number of valence electrons the atom has. So all the atoms in group 1 have 1 valence electron. In group 2, you have 2 valence electrons. I'm going to refer to the groups as the A category for now, or just focus on these elements for now. Group 3A, they have 3 valence electrons. And then all the way here, they have 8 valence electrons. And so those are some good introductions. That's some good navigation tools to find out some important information about an element you might be looking for. Do you have anything else to add?
So groups, vertical columns, number of valence electrons, rows, horizontal periods, horizontal rows is the energy levels, the major energy levels for the orbit for the atom.
Yes, correct. And
That's
so,
worth noting.
yeah, yes.
Like I say, that's worth
noting.
Now I don't have to remember those things. I can just pull it off the periodic table.
Yeah, exactly. So that's kind of starting to go into why chemists really like the periodic table and use it as a helpful tool. So that way you don't have to memorize all of them, all of these elements and all of their properties. to further dive into how the periodic table is organized, we can also consider orbitals. And if we are this far in the course already, we know that there is the s orbital, the p orbital, the d orbital, and the f orbital in that order. And if we look at how the periodic table is arranged, can you help me out here? It's the s orbital atom.
So they're all in the s orbitals, and if I think we've done photoelectron spectroscopy by now, and so those elements all have their electrons, their outer electrons in the 1s, the 2s, the 3s, the 4s, the 5s, the 6s, and the 7s going down those two groups.
Yeah, I think the way I wanted to phrase it, and your phrasing was very helpful as well, but when you fill up valence electrons, the last electrons end up in the s orbital as you fill up the electrons in an energy level.
That might be a better way of saying it. Yeah, that the atom, for those elements in groups 1 and 2, the last orbitals to be filled are the s orbitals, and for hydrogen it's the 1s. For lithium and beryllium it's the 2s. For sodium and magnesium it's the 3s, etc. as you're going down.
Exactly. So this far left-hand side is, I'll just refer to them as the s orbital atoms. If we move over to the right side, 13 through 18 on this periodic table, groups 13 through 18 on this periodic table, if you were to fill up the valence electrons of these orbitals, of these elements, the last valence electrons end up in the p orbital. For example, boron, its electron configuration would be 1s2, 2s2, 2p1. Its last electron in the p orbital. So all of these elements, excluding helium, because hydrogen and helium only have s orbitals, these elements have their last valence electron in the p orbital. And we can also see that pattern with these transition metals right here, where those last valence electrons, as you fill up the energy levels and the orbitals, they end up in the d orbital. And then all the way down here, these are the last few elements that fill up the f orbital. Their last valence electrons fill up the f orbital. And that's also why some periodic tables have their groupings split up as an A and B. 1A, 2A, 1B, 2B, to differentiate between all the different orbitals.
Okay.
And so it's good to be comfortable with this periodic table because you can see all of those patterns, the period, the groups, the orbitals. But there have been other people, other scientists out there who thought this design didn't portray one thing as well, or didn't show the complete pattern or picture. So I'd like to share some other periodic tables with you if you don't mind.
I'm looking forward to it.
All right, so this one is the periodic table, and let me see if I can move this up a little bit. with the lanthanides and actinides inserted, or that f orbital group of elements inserted right in here. And so you can see that it's a lot wider, the element squares are smaller, and so this shows that orbital pattern a little bit better, right? You can see S, F, D, P orbital elements, as I'll refer to them. But for practicality reasons, we end up putting them on the bottom. So that way, when we print out periodic tables on exams, you can still read, you can fit more information into each square. Another different one, which I think is pretty interesting, is this upside down periodic table. You can see that the f orbital, or the lanthanides actinides, are on top, and that instead of reading top down, we go bottom up when we read the elements and we increase atomic number. Hydrogen, helium, lithium, beryllium, so on and so forth. And there was actually a video, an article explaining the creator's intent for this, and perhaps our students might find this pretty helpful compared to the original standard periodic table. But it's to better visualize filling up energy levels. So if I show you this picture right here of the energy levels, right? We have 1s, 2s, 2p, 3s, 3p, so on. You can see that it's in the same direction, starting from bottom up. You put one electron in the 1s, another electron in the 1s orbital, then 2s here, and then 2p, and it sort of simulates that same idea when we fill up energy level diagrams. So far, so good?
Yeah, I've never really looked at this table like this, and makes me think we should use this one all the time. I mean, I think it's an interesting question, because you're absolutely right. It shows it's consistent with our energy level diagrams. It's consistent with the photoelectron spectroscopy we've looked at. It works in terms of all those sorts of things, and it would be nice if we did those consistently. I was thinking that we could turn our energy level diagrams upside down, but then they would be the opposite way they are in every textbook, and every student would again see something different. So yeah.
Yeah.
One way or another, you've got to either flip the table or flip the energy level diagrams.
Yeah, it's a little challenging when going back and forth from our standard periodic table to the energy level diagrams. The only issue with this one, the only argument I've heard, is that many people, referring to people as like most Westerners, read top to bottom, left to right.
Mm-hmm.
And so thorium, element 90, atomic number 90, is not the first element, which hydrogen is the first element. And so perhaps that can confuse students, but that's the only argument I've heard.
Maybe we call it a periodic graph instead of a periodic table, because graphs we often read from the origin, right? From the 0, 0 point, which in your Western left to right, top to bottom world says, let's start down there at the bottom left, right? To figure out what's going on.
Exactly. That's also another point that the inventor mentioned, that this is more like a graph than, as we've been discussing, a table. And it also looks more like a table too, if you think about it. And then finally, this one dating back from the 1950s, featured on the Time magazine, is this very spirally circle periodic table. And I think you can tell it's from the 50s because they only have atomic number, if you look all the way up here, 104. And we've discovered and made many more elements than that so far. But there's a little description because this is, I'm pretty sure, photo scanned from the magazine itself. But basically, the original inventor thought this table would better display the groups and the idea that the valence electrons filling up is a circular pattern, as you can visualize with the many circles.
I mean, I certainly get the impression that hydrogen and helium are smaller than fluorine and neon.
Yes, that's also another great point that I didn't even notice. You can see atomic size better, except with some weird exceptions like radium being a very big atom, but having such a small portion.
Yeah.
And so far. But hopefully, with some of these other periodic tables, you might be able to better visualize some of the other patterns. Maybe you're glad that we don't use this crazy round periodic table to teach you guys elements and the patterns, but hopefully you'll at least start to appreciate and perhaps try to actively familiarize yourself with the periodic table. Would you like to add anything else, Dr. Hunter?
Not really. I mean, there's a lot of information in the table waiting to be used by students and by chemists if they just get comfortable doing that. And so, the best way to get comfortable doing it is to use it a lot. If you Google what's the mass of magnesium, you'll probably find out that it's 24.305, but you won't have right next to it necessarily all this other information that's part of it as well. So if you can learn to get the information off the periodic table, it will help you to understand the ways in which chemists try to understand the world.
Yep, exactly. All right, I think that's all, Dr. Hunter.
So thank you, Kevin.
Thank you, Dr. Hunter. Have a good one.
Okay, all right.